So in this little addendum video, what I wanted to do is give a sort of explanation as to why the law of sines works the way it does. Okay? So the law of sines says if I have a triangle, let's call this angle A, so this is side A, this is angle B, this is side B, here's C and C. So the claim that we are going to now establish why is true is that the sine of A over A is equal to the sine of B over B, which is equal to the sine of C over C. That's the law of sines. But why? All right, so here's my triangle. What I'm going to do, here's angle A, here's angle B, here's side A, here's side B. I said them reverse from how I wrote them. I'm going to drop an altitude. So I drop this imaginary line which is perpendicular to that side. If the triangle is like this, the altitude actually extends out here, but that's okay. It doesn't actually change any of the computations. It just makes the picture look weird. So I'm not drawing it like that. It doesn't really matter, however. So I drop this altitude. I don't know how tall it is. I'm going to call it h for my unknown height. But the point is, now I have two right triangles. So what is the sine of A? Well, here I have a right triangle. So the sine of A is opposite over hypotenuse. H is opposite A, and in that right triangle, the hypotenuse is B, which means H is equal to B times the sine of A. However, in the right triangle, if I take the sine of B, I get H over A, which tells me that H is equal to A times the sine of B. But they're both H. So if two things are both equal to H, they're equal to each other. So B times the sine of, sorry, I should use capital letters for angles. B times the sine of A is equal to A times the sine of B. If I divide both sides by sine A, we end up at B is equal to A times the sine of B over the sine of A. And now I'm going to divide both sides by the sine of B. And there we have it. B over sine B is equal to A over sine A. And if I had done different altitudes, okay, notice that nothing was really special about which side I called C versus A versus B. So instead of dropping this altitude, if I had dropped this one or this one, I would get different equalities. So I could also say, oh, sorry, these are reciprocated from what we were trying to get. So whatever, flip these, fine. You can get the other one involving C. Sorry, the version that I wrote here where the signs are in the denominator is not standard, but you do find it in some sources. And for whatever reason, I always tend to default to that. Typically, you see the signs up in the numerator. The reason being is that you want to be careful about dividing by 0. And side lengths in a triangle are definitely not 0. But what about a sine? Could that be 0? As it turns out, assuming we're talking about actual angles that go into triangles, the only way the sine of an angle could be 0 is if the angle was 0. And what would an angle 0 mean in a triangle? You didn't really have a triangle, you had a flat line. So it doesn't really come up. So for actual applications to completing triangles, it doesn't matter. So I tend to sometimes write it reciprocated, like there at the bottom. It's the same equation as the one up top. Point being, dropping an altitude in any triangle you want, and then expressing the sine of different angles related to the height of that altitude is how you get the law of sines.